Hey everyone, welcome to Chapter 17, Section 2. This section is going to be all about buffer solutions. Alright, so grab your guided notes and let's begin. So we start off with this concept of a buffer. And I use buffers all the time in my lab. They help me calibrate my pH meters whenever we use a pH meter. And what their job is they try to counteract any kind of changes in pH. So after a lab that we've been doing titrations for, and you've been adding acids or bases to my pH meters, all I have to do is dunk them into a buffer solution. And depending on if there's an acid or a base on that little pH probe, the buffer will counteract with the acid or base that is sticking to the pH meter, and it'll basically bring it back to whatever pH I want it to be at, so that I can recalibrate the pH meters over and over and over again. So buffers are very handy in the lab, and basically all they are solutions of a weak conjugate acid-base pair. Very simple to make, and the concept is not too difficult, but setting up the ice table I think is the hardest part. So I want to make sure you understand what's happening when you have a buffer solution and you add a little bit of acid or base to the buffer solution, how it's going to respond. So let's take, for example, an equimolar solution of hydrofluoric acid in sodium fluoride. So that's the buffer, is a combination of hydrofluoric acid with sodium fluoride. So you have a strong a weak acid here with a very strong ionizable ions here. So they fully dissolve here. This is your salt. Basically, it's just a salt and an acid, okay? So look up here. We have an equimolar solution, so the number of moles of HF equals the number of moles of fluoride ions in the solution. Okay, they're equal. But what we're going to do is we're going to add a base, a really strong base that fully ionizes, and so we're adding basically hydroxide ions. Okay, when you add hydroxide ions to a buffer solution that has, say, like an acid in there, the hydroxide will naturally react with HF. And you can therefore expect some of the HF to go away because we reacted OH with it. But when we reacted OH with HF, one of the products of that reaction obviously is water because we're neutralizing the acid. But the other product is the fluoride ion. So your fluoride ion concentration will increase while the acid concentration decreased. Alright, so when you take a buffer and you add a base to it, the acid that's in that buffer will decrease, but the ion will increase. Now let's look at the opposite. What if I add an acid to something that has already got acid in there? Well, the H plus will naturally be drawn towards that fluoride ion, right? So these two are going to interact this time, and therefore the fluorine ion concentration will drop. But when these two react, guess what they make? They make HF, the acid. So the acid will shoot up a little bit in concentration, but the fluorine will decrease a little bit in concentration. And this is essentially a buffer. This is how a buffer responds to the addition of an acid or a base to it. It tries to counteract or counterbalance any kind of pH change. And this is all the Chatelier's principle, so let's keep going here. It says, consider the equilibrium constant expression for the dissociation of a generic acid. Okay, we're going to use the generic formula HA. H is the ionizable hydrogen, A is the ionizable anion, and when you dunk it into water, this is the typical thing we've seen. This is how an acid responds. Okay, so I want you to think about this equilibrium right here. We have an acid, we add it to water, you make some hydronium ions and the anion. Okay, and you know that the Ka expression looks like this. It's always products over reactants. Alright, so let's keep going. I'm going to rearrange slightly, just a little bit, this formula. And when I do so, basically all I did is I took the product, which is on the numerator, I took the product down over here for the hydrogen ion here, and now I've got the A on the numerator and the HA on the denominator. So basically I just took one of the things off of the numerator and put it in front. Okay? It says taking the negative log of this. Right? When you take the negative log of this, I want you to consider what you would get. So we're going to take the negative log of the entire thing. Negative log of Ka will give you pKa. Okay, we learned that in one of the previous sections. And you guys are totally familiar with this, right? Negative log of the concentration of the hydronium ion, that's pH. And then this is the concentration of your base. We always call like the anion the base. And then this is the concentration of your original acid, the acid. Alright, so what am I getting at here? This is a very important formula. What you have basically is pKa is equal to pH minus log concentration base over your acid. And then if you rearrange it just a little bit, you can get two different formulas. You have formula A up on top, you have formula B on the bottom. Basically just rearranging to solve for pH is what this is. And this formula down here is super duper important, and so is the one on top. If I were you, I would just commit both of these to memory and just realize that they both are the same thing, just rearranged. And we call this the Henderson-Hasselbalch equation. Very important equation for buffer solutions. This is something that you should commit to memory. Put it on a flashcard. Associate it with buffers, okay? Very, very important. And I'll show you why. Here's a sample exercise from your book. This is 17.3, and 17.3 is on page 725. The question is, what is the pH of a buffer that is 0.12 molar in lactic acid, and they give you the formula, and 0.10 molar in sodium lactate? So you have lactic acid, a weak acid, just like in the previous example, and you have a salt that has the weak base in there. Okay, the lactate, the anion is called the base. Alright, and then they give you the Ka value is, for lactic acid, is 1.4 times 10 to the negative 4. So when you're tackling these buffer solutions, and obviously this is a buffer, we first need to analyze. It says we're asked to calculate the pH of a buffer containing lactic acid and its conjugate base. So first we're going to plan. It says we will first determine the pH using the method described in section 17.1, the common ion effect, basically, where you're going to have an initial concentration on your anion, okay? Because your sodium lactate, this guy fully ionizes in solution, so therefore that means we are going to have some initial lactate ion in the solution before we reach an equilibrium, okay? So first we're going to do it just the same way we did in chapters in the previous section. And then it says, because this acid, the lactic acid, is a weak electrolyte, and sodium lactate is a strong electrolyte, the major species involved in the solution, again, are the lactic acid, the sodium ion, and the lactate ion, okay? Because this guy is not going to fully ionize. He's a weak acid and therefore doesn't make very much hydrogen ions in solution. It says the sodium ion is a spectator ion, right? Because we don't care about that guy. He's not going to affect the pH in any way. It's really all about these anions. So your conjugate acid-base pair, the acid here, this is your conjugate base here, and the H plus ion is what is really going to help you determine the pH for this guy, okay? So here we go. Here's how we're going to solve this. It says the initial and equilibrium concentration of the species involved in the equation, or in the equilibrium, are like this. Here's your lactic acid, here's your hydrogen ion, and here's your lactate ion here. So your acid's initial concentration, just like we did in the first section, okay? And the equilibrium concentrations are governed by this equilibrium expression. And here's your overall equilibrium expression. You have plus x on the numerator, minus x on the denominator. So we're going to check to see if we can ignore the plus and minus x, as always. And it says because your Ka is so small and a common ion is present, you're going to pretty much expect that that x is really small on the subtractions and the additions right here on the previous screen. So it's okay to ignore those x's. Alright, so you solve for x, and it gives you a value that justifies your approximation of ignoring your x's up here, which is great, that's good. Look at your value of x, it's really small. 1.7 times 10 to the negative 4 molar. Alright, look back at your equilibrium expression and make sure you understand what your X really solved for. Your X solved for the hydrogen ion concentration right here, the H+. Alright, so make sure you keep that straight. So here's your hydrogen ion concentration, therefore all you have to do to figure out pH is negative log it, and so you have 3.77. Alright, and here is where I get to show you that the Henderson-Hasselbalch equation actually works perfect for this entire thing, which is really cool. So pH is equal to your pKa. So remember, in order to get pKa, you're going to have to take the Ka value and negative log it, okay? And then you've got to do the log of the concentration in the base over the concentration of the acid. Your pKa should be 3.85, and you are going to add the log of the base, which is the anion, which is 0.1. Look up here, it's the same thing right here. This was one of your products, the anion, over 0.12, which was the initial concentration of your acid to begin with. Alright, so you do all of that, and look at that. You get the same answer from using an ice table as the Henderson-Hasselbalch equation. Isn't that fabulous? So I've taught you a little trick, and it works pretty much every time for these buffer solutions. It'll save you a lot of time, and you may or may not have to use an ice table anymore. Isn't that nice? Alright, another sample exercise that I want to do is sample exercise 17.4. This is how you prepare a buffer solution. So they specifically ask how many moles of ammonium chloride should be added to 2 liters of a 0.1 molar ammonia solution to form a buffer whose pH is 9. One of the things you should remember is it says that up here it says assume that the addition of the salt does not change the volume. And you guys remember this, when you have a solution at a specific volume, like already set at a specific volume, and it has a specific molarity. If you add a solid into this perfectly measured volume, when you add a solid, that volume is going to go up. It's just like when you sit down into a bathtub, the volume goes up. Well, when you add a salt to a standardized solution at a specific volume, the volume is going to change a little. So it's really important to assume that the volume isn't changing, because if it does, the concentration will actually be less than what you would initially expect. Alright, so let's tackle this problem. There's something that I want to show you that is not in your book. I don't think your book did a very good job showing this example, and that's why I really wanted to talk about it myself. So what you're dealing with is a conjugate acid-base pair. Alright? The equilibrium is specific with dealing with the difference between the ammonia and the ammonium ion. The key to doing this is to pretend that you've got the NH3, the ammonia, reacting with water. Okay, you see that in the practice problem in your book too. That's great. And your equilibrium will look something like this. You got your ammonium ion and your OH ion. So let's think about all the stuff that happens when you make a buffer solution. Alright, the ammonia itself is a really weak acid. It's a very weak acid, doesn't ionize very well. So whatever concentration you started with in this problem up here, look up here, right there, this is the initial concentration of your ammonia. It's not going to change. So if we were to construct an ice table here, there would not be a significant amount of ionization going on with the ammonia. Okay, it's not going to ionize very well. The thing that will definitely ionize when you add it is the ammonium chloride. Alright, so the whole point of this question is how much of this should we add to the solution to make the pH, now mind you, the pH 9. Well, here's the thing. What you have to figure out is if you have a pH of 9, if the pH is equal to 9, what will that make this concentration be? The OH concentration. So think about the pH wheel, alright, and how it works. If you've got the pH to be 9, that's what we're looking for, and at equilibrium we want that pH to be 9. What concentration would you need the OH to be if that pH is 9? Alright, so let's think about what we do know. We do know that this guy should be 0.10 molar at equilibrium because it's not going to ionize very well, so there's no change in X. We don't know the ammonium ion concentration, but using pH, we can definitely figure out what the hydroxide ion's concentration should be at equilibrium. Okay? So let's tackle this problem, and I'm going to use my own version here, okay? Alright, so one of the first things that we need to do is we need to figure out the hydroxide ion solution at equilibrium so that the pH is 9. So we're seeking the pH to be 9. Alright, well, one of the first things that we can do is we can figure out the pOH. That would be 14 minus 9, which is 5, right? And then we can figure out the hydroxide ion solution concentration should be 10 to the negative 5th. Alright, does that so far make sense? Which, guys, that's like 1.0 times 10 to the negative 5th if you want to get technical. So that would be the molarity of the hydroxide ion solution that we need in that equilibrium, okay? And remember what I told you, the ammonium ions concentration? Well, the ammonia does not ionize very well, so the initial concentration is what we're going to use, the 0.1 molar. We're assuming that it did not ionize very well. Alright, so what are you left with? Well, if you go back to this, we know now that this hydroxide ion concentration should be 1.0 times 10 to the negative 5th molar. Okay? So far so good. So now we need to be careful about what we are going to use for our K value. Okay? You have a decision to make. If you're going to use ammonia, right, that's, if you look at the equation, that's what we are using. We're using ammonia. You need to make sure that you're using the Kb value for ammonia. Because if you look in the index and in appendixes, ammonia can actually have a Ka value for the NH4. Alright, so make sure you're using the Kb value, and when you look it up, hold on, the Kb value will be equal to 1.8 times 10 to the negative 5th. And again, that's for your NH3. Okay? So let's go ahead and try to set up the equilibrium expression. Your Kb value, think about the equation that I just gave you. Look at your products. In your products, you will have the NH4 ion. You will have the hydroxide ion. Okay, those are your products. And your reactant is ammonia. Okay? Alright, so let's plug in all of the stuff that we do know that we have. Okay? This guy goes right here. And you've got this guy. I believe it was 0.10 molar, right? Let me just triple check my work here, make sure I'm doing it right. Blah, 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 blah. Pretty sure I've got it right. Alright, so the point of this whole thing is we needed to figure out how much ammonium ion to add to the buffer solution to make the pH specifically 9. Alright, from the pH we figured out the concentration OH that we would need to have at equilibrium. We decided that ammonia wasn't a very strong base and that it wasn't going to ionize very well, and so the initial concentration of ammonia is going to pretty much stay the same, 0.10 molar. Alright, so now all you guys have to do is solve. Okay? Now your book did it slightly different. They rearranged that formula right there to solve for the ammonium ion. So basically they took this and they rearranged it. That's all they did. Okay? So they said that the NH4 ion concentration would be equal to your Kb, which is 1.8 times 10 to the negative 5. And then we got to multiply that by the 0.10 molar up on the numerator. On the denominator you have 1.0 times 10 to the negative 5. Right? So think about how you would flip and rearrange this whole formula to solve for the ammonium ion, okay? So basically that's what they're trying to do, okay? Alright, so they just flipped and rearranged the formula, and when you are careful and you do a good job, you should get 0.18 molar. Now, you got to be careful because in the problem, the solution was not 1 liter. And this is the really hard part for AP students to remember, is to look back at the original question. The original question said that this was a 2-liter solution. Remember, this is the number of moles per liter. That's what molar stands for. Moles per liter. Well, you don't have 1 liter, you have 2 liters. So at the very end, you can't forget to just multiply this by 2. And the true answer, the number of moles required to be added to the solution, should be 0.36 moles of NH4Cl should be added to your buffer solution. Alright, I hope that having me doing this example here this way helped to better explain all of this. Alright, so that was sample exercise 17.4. Okay, moving on. So there's a way that you can attack a problem when you are adding a strong acid or a strong base to a buffer. One of the things that we can do is basically assume that it's safe to assume that all the strong acid or base is consumed in the buffer acid or buffer base reaction. Alright, so here is the diagram. Here's your buffer. It contains a little bit of acid and a little bit of anion. If you add a strong acid to this guy, you can pretty much assume that all of the acid is going to be used up. This X value here will be making, this X right here, this X anion, will be making some HX for you. So you're going to have to recalculate your HX and your X minus concentrations using Ka. Okay, you got to use your Ka. Alright, so all of this part right here is just a stoichiometric calculation, but this part at the end, this part is an equilibrium calculation, okay? So I hope the previous 2 problems, examples kind of helped you out a little bit there. Alright, so for a picture here, this is a picture in your textbook. It says the addition of a strong acid or base to a buffer. Here's basically what will happen. Here's the acid, here's the salt. Okay, the acid is up on top, the salt is on the bottom. When you add some base to this, what is the base going to react with? It's going to react with the acid, right? So when it reacts with the acid, it's going to make an additional salt in the process. Think about a neutralization reaction. Neutralization reactions will always make water and salt. Alright, so when you're adding the base, the concentration of the acid should go down, the concentration of the salt should go up, and you see that accordingly over here. Alright, so let's talk a little bit about when you add an acid to a buffer. So when you add an acid to a buffer, check out what happened to the acid concentration. Here the acid concentration went down and the pH adjusted, and it went down from the, or I'm sorry, the pH adjusted and the hydrogen ion concentration, sorry, the hydrogen ion concentration adjusted, and the pH actually increased with the addition of a base. Think of Le Chatelier's principle. Sorry, I forgot. Alright, now down here when you add an acid, check this out. The H, this is your acid, the acid concentration will increase slightly. Your salt concentration, because you added the acid to that, the H plus will react here and the H and your acid solution will go up, and then your salt solution will go down, and notice the pH did drop a little bit from the original. Okay, so when you add a base to a buffer, pH goes up. When you add an acid to a buffer, pH will go down. Alright, it always says to use the Henderson-Hasselbalch equation to determine the new pH of your solution, okay? Alright, now, calculating pH changes in buffers. I don't think this is a duplicate. I triple checked here. So this corresponds, I think, with the sample exercise 17.5, but I just put it into my PowerPoint like this. It says a buffer is made by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate to enough water to make a 1 liter. You're lucky you have a 1 liter solution this time. And the pH of the buffer is 4.74. Calculate the pH of the solution after 0.02 moles of sodium hydroxide is added. Okay, so before the reaction, your acid moles, the number of moles of acid is equal to the number of moles of the salt base. Okay, they did that on purpose because anytime you have that, it makes it really nice to calculate your pH and your pKa. Okay, the pH of this buffer solution, go back, is 4.74. Alright, so 4.74, remember what this means. In your buffer solution, basically what you have, hold on, you have HC2H3O2, and you're going to have the H plus popping off, and then you've got the C2H3O2 ion. Okay, this is what we're looking at. So in order to get, in order to figure out this guy, you need to realize that they gave you a nice little tidbit of information there. What they did is they gave you your pH of the buffer at the very end. Okay? Alright, so your pH is equal to 4.74, and it says the 0.2 mole of NaOH is going to react with the 0.2 mole of your acetic acid. So the acid-base reaction is still in place, okay? So you've got your acid going on here, you got your base going on there. You're going to make a little bit more of the anion, the salt. The base, that's what we call the anion of the salt is what we call the base. And you've got the water. Alright, so before the reaction occurs, here is the initial concentration of, or the initial number of moles of your acid. Here's your initial number of moles of your base. Okay, so these are the initials. And where did we pull this from? The OH concentration. Where do we get that from? The 0.02 mole of the NaOH is what was added to the buffer. So we're figuring out the new pH after we add the base to this. Okay, so your OH concentration right here, 0.020. That's what they added, and we want to see what effect that's going to have. Alright, so after the reaction, what you need to realize is that this OH is going to react with your acid, right? So come back over to your moles, and you need to decrease the concentration here, right here, by 0.02, because this is what it's going to do. It's going to react, and it's on the reactant side, so the concentration of your acid will go down by whatever the number of moles of hydroxide ion there was, okay? So you'll notice that this guy went down. But on the product side, you increased by this amount right here, because we're assuming that all of this base was consumed, right? When you added it to the buffer, all of this base was consumed. So whatever concentration was lost over here to this acid, that's whatever was gained right here by this anion right there. Alright? So you'll notice that we increased this guy by 0.320 mole. And notice after the reaction, all of this OH is out. It's gone. Okay? Alright, so now we're going to use that Henderson-Hasselbalch equation, or if you really want to, you can set up an ice table, but trust me, the Henderson-Hasselbalch equation is a lot easier. Alright, so what we've got is the pH is going to be equal to 4.74 plus the log of, always remember how it goes, okay, because this is important. The equation, one more time, is on page 725 at the top. So what we've got is the pKa is 4.74. We're going to add that to the log of the base on the top. Remember, the base for you guys is the anion. Okay, so the anion increased by 0.02, so it's 0.320. And then you've got the acid on the bottom, which was 0.20. Alright, and all you have to do is figure this out, the log, and notice the tiny little change here, 0.06 due to this. So the new pH is just 4.80. That's it.